So think about limits, and we have a few limit laws that are going to be going to play into this discussion. So none of this is new, and in fact, these slides are copied from exactly the presentation I made to you last semester on limits. So if we have a limit of as x approaches a of two functions, it's going to be the limit of that function approaching, of each of the functions individually approaching a. This should be a, not b. This should be a. Okay, so the sum of two functions taken to a limit is the same thing as taking the limit of those two functions, and it also works for subtraction as well. When we're finding the limits of, I guess I already changed that, corrected that a, but anyway, I'll fix that when I post it. If we have a constant times a function, we can just take the constant out and then find the limit of the function. So in other words, that constant doesn't change with x as x changes, so it just turns out to be a constant in front of the limit. And then if we have the product of two limits, and here's the confusing one, because if we take two functions and multiply them together and take the limit as x goes to a, we can take the limits individually of these things as it goes to a and multiply them together. And the reason why I say this is confusing is because we know that with derivatives this isn't the case. You have to use the product rule with a derivative, but not with a limit. So okay, with a limit it just goes there. With derivatives it doesn't. You have to actually use the product rule, which, if you recall, involves the sum of two expressions. And then we have, with a ratio, it works the same way. We can take the ratio of the limits, so long as the limit as g of x doesn't go to 0, because then we have division by 0. Okay, so those are kind of the nuts and bolts limit kind of things, and I'm going to use them in just a little bit to demonstrate the limit of, or the derivative of sine. Okay, so a couple theorems. Okay, so if f is always less than g at x, where x is near a, except possibly a, then, and the limit of both of them exists, then the limit is also going to be less than or equal to the function. Okay, so what that means is that if I am at any age always shorter than my brother, and my brother and I grow up, that means by the time we reach our ultimate ages, I'm going to be either shorter than him or equal to him, right? If I'm always either equal or shorter than him, my ultimate limit as x goes to any number is, that relationship's going to hold. Now that's not nearly as interesting, though, as the squeeze theorem. If we apply the squeeze theorem twice, if we're looking at a function that's between two functions, like g is in between f and h for all values of x, except possibly at a, and the limit of f and the limit of h equals L, what the theorem says is that the value in between goes to L as well. And so if you think about the squeeze theorem as maybe if I have some function that's decreasing but then leveling off at some point, and another function that is increasing but perhaps leveling off at some point. Okay, any function that's in between, so long as it's always less than this one and greater than this, the limits ultimately, they'll all be the same. So this is going to be useful in a number of ways. So it's going to be one of those useful things. You know, the squeeze theorem, I didn't actually prove it. The proof is in the book, I believe, but it's one of those things that intuitively makes sense. You know, that if a function's always between two functions, and these two, the outer and the upper and the lower function, ultimately limit out to a particular value, the one in the middle is going to be that value as well, so long as it's always in between the two functions. Okay, so let's look at the derivative definition again. This is that notation where we're going to look at the derivative is the rate of change of a function with respect to the variable. And so the actual definition of it is going to be the difference quotient as h approaches 0. And all of you know this because all of you wrote it on your final exams, right? Okay, so rather than going over all the differentiation rules, I posted this on Moodle, and for today I have it as a handout here. All the differentiation rules that we had were the derivative of a constant, derivative of a variable, the sum, difference, product rules. In fact, I think I gave this to you last semester.
Yeah, you did.
And so, just to go over them really quickly, the first one is the derivative of a constant is 0. The derivative of a constant times a function is the constant times the derivative of the function. The derivative of the variable x is 1. Then we have the sum and differences, that the derivative of the sum of functions and the difference of functions are the sums of the derivatives. The power rule, remember that one? And then the product rule, we actually take that two-term thing where we take the derivative of f times g is going to be f prime g plus f g prime. And then the quotient rule is the one where we have the ratio of the two functions, and so f prime g minus f g prime over g squared. And then the chain rule, which is the composite, f composite g is going to be the derivative of f composite g times the derivative of g. And then the rest is basically just alternate notation. But those things I know you knew pretty well last semester because you all passed the gateway. And so now what I want to do is look at the derivative of the sine of x. And so when I put this into the derivative definition, there's a couple things that come to play here. Number one, you can see one of the applications of the rule where we have the sum of angles in the sine. But before we even get there, let's take a look qualitatively at what the derivative should look like for sine. So we have the sine goes through something like this, and it continues back this way, where this is 0, this is going to be 2, pi over 2, I mean. And then this is going to be pi, 3 pi over 2, and 2 pi. And this will be negative pi over 2. Remember, that's the derivative. So if we look qualitatively, we would expect the derivative to be its maximum at 0 at pi and at 2 pi. And we'd expect it to be 0 at pi over 2 and 3 pi over 2. So let's look at the cosine function now. Is there a different color marker around somewhere? I'll use this black one. Okay, so if I graph the cosine, look what I have here. It reaches its maximum where the derivative of the sine should reach its maximum, where the derivative of the sine is 0, the cosine is 0, where the derivative of the sine is at its most negative value. Here we're down here. When the derivative of the sine equals 0, cosine equals 0, and then back up here where we have our steepest part of the slope is where the cosine's at its maximum. So qualitatively, we can expect that the cosine is going to be the derivative of the sine, right? It's just shifted over a little bit. The shape is there. But how do we know it's exactly that? Maybe some, more extreme version of it, or something that varies a little bit more than just at those 3 points. We still need to prove it analytically, but at least we have some expectation that either cosine or something that looks very much like the cosine will be the derivative. So I'm going to go through this process here. First, I'm going to apply the rule the angle addition rule for sine, and so I get sine of x cosine of h plus cosine of x sine of h, and then we have the minus x that's going to be trailing from here. And then I'm just going to rewrite the order of the terms. That's all I've done here. So I put this negative sign in the middle, and I put this cosine of x sine of h at the end here. So it's just a rewrite at this point. I'll let you catch up here. All right. So then now I'm going to factor out the sine of x from the first 2 terms here. You see I have the sine of x cosine h minus the sine of x, and that becomes the sine of x times cosine h minus 1, and I'm leaving this term alone here, cosine x sine h. All right. Now I'm just going to rewrite it so it looks a little different in form. I didn't do any algebra here. This is just a rewrite of exactly the same thing. I'm splitting up the 2 parts of the numerator into 2 different fractions. And the first one is sine x cosine h minus 1 over h. And so I choose to write it this way. And then on this particular one, I'm going to write as cosine x times sine of h over h. Okay, so one of the things that we can do, and the reason why I showed you those limit rules again, is that we can look at each one of these factors and decide what the limits are individually, and then decide what the function or what the derivative should look like. So as h goes to 0, the sine of x is constant, right? So x isn't our variable for the purposes of calculating the derivative. H is. And so x here, the sine of x doesn't vary with h, and so the limit as h goes to 0 is just plain old sine of x. Now this one is a little bit more complicated. We're going to take a look at that a little bit later. But for the same reason why the sine of x is constant, so is the cosine of x. So if I then rewrite it, breaking up my limits into 2 sums, I get this. And here I'm just using my limit laws, and I've taken the limit as h goes to 0 of sine of x and a cosine of x, and those are treated as constants. And then I have these 2 limits that I need to evaluate. And so these don't necessarily intuitively evaluate, right? Because as h goes to 0, the sine of h goes to 0 over 0. So 0 over 0 is what's called an indeterminate form. So we need to look at it some other way. Same with cosine of h. Cosine of h, as h goes to 0, is going to be 1 minus 1 over 0, and we have that same indeterminate form. So I'm going to look first at this particular expression, and then I'll return to the cosine h minus 1 over h next. Okay, so let's look at our unit circle. And so the radius is 1, and so this distance, a to b here, is the sine of theta. The distance CB, or CD, excuse me, is the tangent of theta. And this arc, which goes from A to D, is going to be theta when theta is expressed in radians, right? The arc length and the angle in the unit circle are the same thing. So everybody follow me here? You're understanding what this is all about? You see that the line segment AB is the sine of theta? Okay, so I'm going to make an assertion here, and there's a geometric proof in the text, and you can find it elsewhere. But I'm going to just basically do this by eyeball. Okay, so I'm going to say the sine of theta, which is the distance from A to B, is shorter than the distance from A to AD. Right? Here I have a straight line. Here I have a curved line. So no matter how close I get theta to 0 still, the sine of theta is always going to be less than theta. And by the same reasoning, this arc AD is going to be less than the straight line CD. So the tangent of theta is always greater than theta. And this is not mathematically sound at all. I'm making an assertion based on this diagram just so you can get, so we can get to the actual proof. The actual proof of these things are true. The actual proof of it, you can look in the text for that. Okay, so I'm going to rearrange the sine of theta is less than theta by saying that the sine of theta over theta is always less than 1. I'm going to do kind of the same thing. I'll rewrite theta as less than the tangent, and so I'll translate that into sines and cosines, and then from here I'm going to multiply both sides by cosine, divide both sides by theta, and I get this cosine is less than sine of theta over theta. And so I have this expression now where the sine of theta over theta is going to be somewhere between the cosine of theta and 1. Okay, so now what I want to do, since I have this form, remember I had that sine of h over h, I want to figure out what that is. So let me take the limit of this thing as theta goes to 0. And so I know that the limit of, as theta goes to 0 of the cosine is going to be 1, and that this relationship is always true. So if the limit of cosine of theta equals 1, and the other side is 1, I have this situation here where the squeeze theorem said that the limit as theta goes to 0 of sine of theta over theta is going to be 1. Okay, so now I have 3 out of the 4 terms that I had in that limit that I needed. Okay, you with me?
So you're applying the squeeze theorem only to that sine theta over theta? You're applying it to that term?
Yeah, so I'll write it out a little bit more explicitly. So if I have the cosine of theta is less than the sine of theta over theta is less than 1, the limit as theta goes to 0 of cosine of theta equals 1. The limit as theta goes to 0 of 1 is going to be 1. So therefore, by the squeeze theorem, we have the limit as theta goes to 0 of the sine of theta over theta. It's always going to be between these two values, and the two values are the same, so it's going to equal 1. So the squeeze theorem gives us that limit of sine theta over theta. Theta, of course, is measured in radians, and that's crucial to this. Okay, so let's look at this other term, this cosine of h minus 1 over h. The standard way that we're going to handle something like that is we multiply the numerator and the denominator by the conjugate, because then we get this nice thing of cosine squared h minus 1 over h cosine h plus 1. And notice that numerator now, we can make the substitution of negative sine squared of h. And so at this point then, I'm going to rewrite it. And this is just a rewriting by separating out the sine squared of h over some, well, I'm just rewriting it. It's essentially the same thing. And so now that I have the ratio of things, and I know some limits, I know that the limit as h approaches 0 of this thing is going to be negative 1, right? Because the sine of h over h as h approaches 0 is going to be 1, and so we have negative 1. The sine of h approaches 0 as h approaches 0, and then the cosine of h plus 1 is going to be 1. So I have negative 1 times 0 over 1, a perfectly good calculatable value. I don't get anything tricky of dividing by 0 or anything like that. I get it to equal 0. So this expression that we had in that derivative formula is now 0. Okay, everybody get this? Well, do you understand it, I guess, is my question. Not at all.
I'm just writing.
Yeah, okay, well let me
Okay.
recap it, okay? Because I think it's important. So this is the term in question, this cosine h minus 1 over h. So the first thing I'm doing here is I'm multiplying it by its conjugate over its conjugate, right? This is just times 1. And then I FOIL that top expression, so I get cosine h minus 1 over the denominator. And then I notice that by my identities, this is going to be negative sine squared of h, right? Because 1 minus the cosine squared of h is sine, so I'm going to make it negative. And then I'm going to write the sine squared of h out twice. Okay, so I have sine of h times the sine of h over the denominator. Now I'm going to group these so that I can see that this is a value that I just calculated. The limit as h goes to 0 of sine of h over h is 1, so I know that one is negative 1. The sine of h is going to be 0 as h approaches 0, and cosine of h as h approaches 0 is going to be 1 plus 1. So this is actually going to be a 2 down here, excuse me. This is a 2. That's a 2, but nevertheless, the value is still 0. Yeah.
I missed what you just said. So how exactly do we know that it's 2?
Because I have the cosine of h as h approaches 0 is 1.
Yeah.
1 plus 1 is 2.
Oh, yeah.
Okay? Don't worry, I missed it the first time too.
Wait, I mean, if it's 0, how, I don't understand. If it's 0, how is it, I mean, because the top is just 0 and the bottom is 1 with an h?
Well, I've taken all these terms. Remember, with limits, I have the product and the quotient rules that I can evaluate these things individually or together and then take the product or the quotient of all the individual terms.
But if you got the sine of nothing or the cosine of nothing,
Well, it's not nothing, it's 0. Sine of 0 is 0, but I have this whole expression of sine of h over h, which on the previous page I said was 1.
Okay.
Okay, so now I have this as 1, but I have a negative in front of it, so that's negative 1. And this is going to be times the sine of h, which as h approaches 0, sine is 0. And as the cosine of h goes to 0, that becomes 1 plus 1, and I get 2. So I have negative 1 times 0 divided by 2.
Okay.
So let's go back to that, that expression that I got for the derivative of sine. And so now I have all these terms. The derivative is the sine of x times 0 plus the cosine of x times 1. And lo and behold, we have the derivative of the sine of x is the cosine of x. Shock of shocks, right? A lot of work for a small conclusion, but it's an important conclusion. Okay, so this is something that, this particular relationship, the sine, or the derivative of the sine of x is going to be the cosine of x. I'm not going to expect you to recreate that, okay? But I think it's important that you have followed it. Now we're going to get the derivatives of the other functions, including cosine, because we don't know the derivative of cosine yet. And these I expect that you should be able to recreate. In fact, you're actually going to do 4 of them in class here. But I'm going to do the derivative of cosine next. Okay, first before we get there, we're going to look at another identity. The sine of x plus pi over 2. A lot of times trig books have this as one of these fundamental identities. Notice I haven't given it to you as an identity because I feel like you should be able to get to it. You use the angle addition formula, which you will be given, and then you evaluate the cosine of pi over 2 and the sine of pi over 2, that's 0 and 1. And so what we have here is that we have this nice identity that has the sine of x plus pi over 2 equals cosine of x. I'm going to do the same thing with the cosine of x plus pi over 2. And I get, by the cosine addition formula, I have cosine of x times 0 minus the sine of x times 1. And so we have these two identities here. So I'm going to write these on the board just so you'll know them. Okay, so now I still have this here. Think about what this means. When I graph this thing, remember I have a starting point which is minus c over b. b is 1, so my starting point is going to be negative pi over 2, and I get my sine curve from there. Well, that's exactly what I drew as the cosine, all right? So this shouldn't be a big leap, right? This is from this kind of graphing and understanding what this pi over 2 does, it shifts everything back a half pi. You get this relationship. Same thing with cosine. If we do that again with cosine, if we move it back half pi over 2, we're going to get negative sine. This is negative, like in my slide. So when I move the cosine back, I'm going to have this black line going like this, which is just the negative of the sine, which is the blue line. Not an identity that is difficult to derive. I'm not going to put it on the identity sheets, but remember that it's there available for you if you want to look it up or derive it if you're doing some other work. Okay, everybody have this down? So with these identities, what I'm going to do is I'm going to, since I know the derivative of sine, I'm going to try and take the derivative of the cosine, okay, because I have something that I can change the form to. Okay. So, if the function is cosine of x, then the derivative with respect to x, I'm going to make a substitution and say, I don't know what the derivative of cosine is. I'm going to take the derivative of sine x plus pi over 2. All right, how do we do the derivative of this thing? Well, we use the chain rule. So when we do the chain rule, it's the derivative of the outer function. In this case, the outer function is sine, right? So the derivative of sine is cosine. The inner function, the x plus pi over 2, the derivative of that, the derivative of x is 1, the derivative of pi over 2 is 0. So we just have times 1, and so we have this expression. The derivative of the cosine now is the cosine of x plus pi over 2, but by the second identity here, we make the substitution back and we say the derivative of the cosine is negative sine of x. All right, so this is kind of a handy thing now when you think about it. If we take successive derivatives, so we take f at x equals the sine of x. If we have f at x equals the sine of x, then we know that the first derivative is going to be the cosine of x. The second derivative is the derivative of cosine, which is negative sine of x. The third derivative now, is going to be the derivative of negative sine of x, which is negative cosine of x. The fourth derivative is going to be the derivative of negative cosine x, which is now going to be the sine of x. And so we keep on going through this cycle where we have infinitely many derivatives of the sine of x, and it goes through this cycle of sine, cosine, negative cosine, sine, and cosine, and so on. So this is kind of a handy thing to know. All right, so we have these two derivatives. I think this is a good exercise for you to do. Find the derivative, let's say, of tangent. Okay, let's do that one first. All right, I'll give you a few minutes to do that. You should look at the large hint here is write it in terms of sine and cosine, and then use the quotient rule.